Hello guys, in this lecture series, we are discussing in complex analysis volume 2. Complex analysis in volume 2, up to the last lecture, I discussed about the expansion of function. Expansion of function. If fz is analytic, then we can expand this function in form of infinite series, as I told you. There are two processes. First, I tell you that is Taylor's theorem. If function is analytic in a closed region C, then I told you fz equal to sigma n equal to 0 to infinity a n z minus a power n. This is infinite expansion in powers of z minus a, or you can say that is expansion of given function by Taylor's theorem about point A or in neighborhood of point A, where a n is defined as, that is factorial n 2 pi I integral c f w minus z dw. This is n minus this. This is power 2 power derivative. This is f w and w minus a to power n plus 1 t. This is the coefficient. That this is the first theorem, and second theorem I told you in last lecture, that is Laurent's theorem. If here function is analytic in a closed region C and A is any point inside C, Laurent's theorem, if we have the region, annular region bounded by two circles C1, C2, this is C1, this is C2, and point is, that is any point in this region, then fz can be expanded by n equal to 0 to infinity a n z minus a to power n plus sigma n equal to 1 to infinity b n z minus n to power minus n. This is the other expansion of analytic function, and this is similar part, but this is part containing negative power of z minus a up to infinite, and this is actually called principal part of Laurent's theorem. If this, I discussed on this theorem, I stated both theorems and I proved both theorems. So please, because proof of both theorems is a part of your curriculum, your syllabus, so you have to prepare, you have to check what is the proof. Both proof I done with the help of Cauchy's integral formula. That is very simple method. Also, there are a number of methods in various books, but these methods I used to prove these are very simple and very short. Now, today, first of all, I will take up a numerical example based on Taylor's theorem and Laurent's theorem. If you see that in Taylor's theorem, that containing only positive power of z minus a, because a is a point. About that, you have to expand given function in both cases. But in Laurent series, you have the positive powers of z minus a as well as negative power of z minus a. So here I will take a numerical example how you can expand a given function in form of Taylor series and Laurent series. Take example. That is expand in Taylor's series and Laurent series fz given by 1 upon z square minus 3z plus 2 in the region A, mod z is less than 1, B, 1 is less than z, mod less than 2, C, mod z is greater than 2 and t 0 is less than mod z minus 1 is less than 1. These are the three regions in which we have to expand given function in form of Laurent series and Taylor series. And here function is given this. So actually, to solve such type of numerical example, there is also very small, very simple technique by which you can expand this. Either you use this, abstract this, and take this function and by the given formula, Taylor's and Laurent, calculate A n and B n. These are very lazy methods. Simple method is that because we proved that formulate that expansion by the help of Cauchy's integral formula as well as binomial theorem, or depending upon the convergence of this. So you know that by binomial theorem, if we have any function like that, so we can expand this 1 minus z plus z square plus 1 if this condition holds. This is the condition of convergence. If mod z is less than 1, that is the you know that common ratio of, because this is a type of GP. So if common ratio less than that, we can expand this in common. So we use this technique to expand this, and in this expansion, if we get only positive power, then we say that that is Taylor's expansion, Taylor's series. If we get positive and negative both power or only negative power, then we can say that it is Laurent expansion. How possible? First, here is, first you expand this, this is factorize this is z minus 1 and z minus 2. And by partial fraction, it is z minus 2 minus z minus 1 by partial fraction. Right? This take it as equation number 1. Now, for first region, for region A. Region A is mod z is less than 1. So, this implies that mod z upon 2 is less than 1 by 2, that is less than 1. So, from 1, we have fz equal to 1 upon z minus 2 and z minus 1. Now, transform this into this form for using binomial theorem. So, from here, we take 1 by 2 common and take it in numerator, that is 1 minus z by 2 whole power minus 1. Here we take simply minus 1, that is plus 1, and this is 1 minus z to power minus 1. Now here mod z minus 2 is less than 1 and mod z is less than 1. So by binomial theorem, we can expand this minus 1 by 2, 1 plus z by 2 plus z square by 2 square plus z cube by 2 cube and so on. In second bracket, all terms again positive, 1 plus z square plus z cube plus 1. If you calculate further, finally we get the result, that is fz equal to, in first bracket, multiply minus 1 by 2 minus 1 by 2 minus z by 4 minus z square by 8 minus z cube by 16 and so on. In second bracket, 1 plus z square by 2 plus z cube by 3 and so on. You calculate 1 minus half is equal to half. Z, this is equal to 3 plus 3 by 4 z. This is again 7 by 8 z square and so on. This is your the answer of the first part of the question, that is the expansion of given function for the region mod z equal to mod z is less than 1. And you see that this expansion, this series is containing only positive power of z. So you can say that this is a Taylor's series because it is containing only positive power of z. So you can see it is a Taylor series, or you can see it as expansion of given function about point z equal to 0. Similarly, if we take second region for B, what is B? 1 is less than mod z is less than 2. If you break B, this equality, so this means mod z is greater than 1 and mod z is less than 2. So for this can be written as 1 by mod z is less than 1. And this is, if we divide 2, mod z by 2 is less than 2. Now, we have this region, these inequalities under which we have to expand given function. And from 1, we have fz equal to 1 upon z minus 2 minus z minus 1. Here, z2, simply you take minus 1 by 2 as a common, 1 minus z by 2 power minus 1 due to this region, bivalent theorem. And here, 1 upon z, so we have to common 1 upon z, then 1 minus 1 by z to power minus 1. Again, similarly, we have calculated mod z less than 1 and 1 upon mod z is less than 1. Both common ratios are less than 1. So, we can use binomial theorem. So, by binomial theorem, it can be expanded 1 plus z by 2 plus z square by 2 square plus z cube by 2 cube plus 1. Here, minus 1 by z, 1 plus 1 by z, 1 upon z square, 1 upon z cube and plus 1. In both cases, because this is negative, all terms are positive, this is negative, all terms are positive. Now, calculate again both brackets, finally, we get the required expansion. Open the bracket, that is minus 2, 1 by 2 z by 4 minus, that is minus, because minus 1 by 2 is taking inside it. That is minus z square by 8 minus z cube by 16 minus 1. In second bracket, again minus 1 by z is inside the bracket. This is minus 1 by z minus 1 by z square minus 1 by z cube and so on. Minus 1 by 2 is 1. So here 1 minus z by 4 minus z square by 8 plus 1. In second bracket, this is minus half minus 1 by 2. In second bracket, that is 1 by z means z to power minus 1, z to power minus 2 and so on. So here you see that this is your required expansion of given function for this region B. Mod z is greater than 1 and less than 2. So, and we see that here this part is containing positive power of z and this part is containing negative power of z. So we can say that it is a Laurent series for given region because this is containing positive and negative both power, and that is the answer of the B part of the question, second part. And now similarly we take third part, C part, given that mod z is greater than 2. Mod z is greater than 2 means 1 upon mod z is less than 1 by 2, that is less than 1. This is the expression. So again, from equation 1, we have fz equal to z minus 2, z minus 1. This is expression, mod z is 2, this is, you can say in other way, this is mod z by 2 is greater than 1 that means 2 upon mod z is less than 1. And also, first case, mod z is greater than 2, then 1 upon mod z is less than 1 by 2, less than 1. Both. In this case, here we take z as a common out, then this is 1 minus 2 upon z whole power minus 1 if you take it in numerator. From here, we have to common again 1 by z, that is 1 minus 1 by z to power minus 1. Now, both conditions here, common ratio 2 by z, that is less than 1. This is, and here 1 by z is again less than 1. Both conditions are satisfying for binomial theorem. Again, by binomial theorem, this will be expanded as 2 upon z, 2 square upon z square, 2 cube upon z cube plus 1. From here, 1 by z, 1 plus 1 by z plus 1 by z square, and so on. Open the bracket, that is 1 by z plus 2 upon z square plus 2 square upon 2 square means 4 upon z cube, and so on. Here, minus 1 by z minus 1 by z square minus 1 by z cube, and so on. If you combine this cancel out, and final expansion is fz equal to first term 2 by z square minus 1 by z square means 1 by z square, 4 by z cube, this is means 3 by z cube, and so on. This is your final expansion. For this region, mod z is greater than 2. And you see that this expansion is containing only negative powers. And so it is also a Laurent series. Laurent series. And that is the answer of third part. Now, we take last part, that is the D part. If region is given by this, 0 is less than mod z minus 1 is less than 1. Right? Your point changes. In these three parts, expansion about to region z minus 0. But in this part is, so first we take, let us consider z minus 1 equal to w. Then region is 0 is mod w is less than 1. And this means mod w is greater than 0 and mod w is less than. Now from 1 we have fz equal to 1 upon z minus 2 minus z minus 1. So first we change z in terms of w by this substitution. From here we have z means w plus 1 minus 2 minus w plus 1 minus 1. Then this is w minus 1 and this is 1 minus w. Now only we have to this, so this can be written as, if we take common minus 1, then this is 1 minus w minus 1 and minus 1 by w. Simply mod w is less than 1, so expand by Ben's theorem, that is 1 plus w square plus w cube plus 1 minus 1 by w. Now, so this is your required expansion. Now substitute the value of w, that is minus 1 plus z minus 1, z minus 1 square, and so on. This is z minus 1. And we see that again in this expansion, positive power of z minus containing and also one negative power. So it is again a Laurent series, right? If point at which you have to expand is shifted to another point, then we can take substitution and solve easily by this. These are the four possibilities, four cases in which you have to expand the given and a function in form of Taylor's theorem and Laurent's theorem. And that is the very simplest method. He used binomial theorem always, after taking common ratio is always less than 1. If you get in the expansion only positive power, then that is Taylor's expansion. If you get positive and negative power both are only negative power, then that is Laurent series. That is the process of this. When now you try same questions, and that is very simple topic, and always you will get an examination. I think 5 to 10 marks according to the BBD University. Now, come on the next topic. That is the next topic of this chapter, this module. That is the calculus of residue. Calculus of residue. Calculus of residue, actually this is very important topic, and individually it is important, and that is very, you can say, applicable topic, and in this topic, by the help of calculus of residue, there is a theorem, complex residue theorem. By that theorem, we can also solve some extraordinary complex integrals. First, we define here what is the zeros and singularity of complex function fz. In last chapter, I just introduced zeros and some singularity, but here I will discuss in detail zeros. First thing, zeros. What is zeros? Actually, if we have a function fz, if this function fz is 0, then values of z are called zeros of fz. Right? For example, if we have fz equal to z square minus 4, if we put fz equal to 0, then we get z equal to plus minus 2. Now, plus minus 2, z barabar minus 2 and z barabar plus 2 are zeros of fz. And there are two types of zeros, isolated zeros and non-isolated zeros. Isolated, non-isolated zeros means if z equal to, if we take z equal to minus 2, z equal to minus 2 is a 0. If no other 0 exists in the neighborhood of this, then this is isolated 0. If in their neighborhood, if in its neighborhood, some other zeros exist, then it is called non-isolated 0. Right? This is the first thing. Second thing, very important, that is very useful to find residue, that is the singularity. Singularity of fz, or you can say singular point of fz. Both are same. Singularity or singular point of fz. First thing, what is the singularity? Actually, singularity is a point at which fz is not at. Simply, if we define, then you can say singularity of fz is a point, simply, at which fz is not analytic. I have discussed what is the analyticity of a function in detail up to the last lecture. If any point at which function is not analytic, then we say that that is a singular point, or you can say this is a singularity of fz. Singular point or singularity of fz. For example, if we take any function, suppose we take a function fz equal to z plus 7 upon z square minus 5z plus 6. This is a function. So we see that in this point if this 5z plus 6 is 0, at that point fz tending to infinity. That means fz is not analytic. And now solve this by factorization. This is z minus 2, z minus 3 equal to 0. So these 2 points z equal to 2 and 3, these are the singular point. Because at these 2 points, as it is not analytic, we can say that these are singular points, are singularity of fz. This is the basic concept, basic fundament of a singular point or singularity. Any point at which fz is not analytic, then function, that point is known as singular point or singularity. And now there are number of types of singularities we have to study it, because basic two singularity basic type are 2 types. One is isolated singularity. Another is non-isolated. Non-isolated singularity. Right? Singularity means a point at which fz is not analytic. Basically, this is of 2 types. One is isolated singularity, and there is non-isolated singularity. Isolated singularity means क्या? What is that? Is if z equal to a is a point at which fz is not analytic. So this is isolated singularity if fz is also not analytic in neighborhood of A. Means fz is not analytic at point A. That is the main condition. That is the main condition, because point A is singular point. Now, along with this point, if we neighborhood, what is the neighborhood? You know that if we take this point and around this we draw a small circle, that is very small circle, means radius is always tending to 0. So this region, number of points existing in this region, and these points are called neighboring points of point A. If in these points, at these points, the function is not analytic, then this is in this point, if function is analytic, then this is isolated singularity. Means z equal to a was the only point at which function is analytic, but on this point function is analytic. Then this is isolated singularity. Otherwise non-isolated. Otherwise means function is not analytic, point A, as well as in neighborhood of A. Neighborhood means if we draw about point A, a small circle, these points are known as neighboring points of point A. If these are also singular points, then we say that this is non-isolated singularity. Right? Means in case of singularity, when it is isolated, then there is a possibility of analyticity in the neighborhood. But if any point is non-isolated singularity, then that means fz is analytic surely, and now it is not analytic, and now that not analyticity property cannot be converted into the analyticity property, because it is non-isolated singularity. Means function is not analytic at that point, as well as in the neighborhood of that point. These are 2 main types. Now, in our syllabus, isolated singularity is further of 3 types. One is removable similarity, another is essential similarity, and thirdly, poles. These are the three types. And now in next lecture, first I will discuss the different types of isolated similarity. As I told you, poles, removable similarity, and essential similarity. And then I will take some examples given of examples of function where your similarity is as a pole or removable similarity or essential similarity, and then we define this. Then in this chapter, that is the heading of this chapter, calculus of residue, then I will define what is residue at pole, because residue will be defined on the pole. And but with the help of residue, we can find the some extraordinary type of complex integral. Okay, thank you.